this video, we are going to look into how quantum mechanics deals with momentum. We have seen earlier about linear momentum, angular momentum, and similar concepts in classical or Newtonian mechanics. Now we are going to explore how momentum is seen into the quantum realm. We are also going to see how classical mechanics and quantum mechanics deals momentum in two different ways. Thereby we will understand how it is different, how the operators comes in, and how we can define momentum in quantum mechanics. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to explore momentum in the realm of quantum mechanics. So first let us see what are the topics that we are covering today. So we are covering these topics. We first understand what is momentum in classical mechanics, how it is different from quantum mechanics, what are the different operators that we use along with the eigen values, and what is called calculating expectation values. These are the few topics that we are going to look into, but primarily we are going to emphasize and see details about momentum in quantum mechanics. So first let us see momentum in terms of classical and quantum and how this can be dealt with it. So momentum, if I see in classical mechanics, is called as more specifically linear momentum or transitional momentum, is the product of the mass and velocity of an object. It is a vector quantity possessing a magnitude and a direction, and if m is an object's mass and v is the velocity, also vector quantity, then the object's momentum p is given as mass times velocity. In the International System of Units, the unit of measurement of momentum is the kilogram meter per second, which is equivalent to the Newton second. Now obviously this figure shows that we are only dealing with one particular mass and velocity, but momentum of system of particles, for example m1, m2 and so on, is the vector sum of their momenta. If two particles, for example, have m1 and m2 as respective masses with velocity v1 and v2, then we can do as the calculation as this: v1 plus v2 plus m1 v1 plus m1 v2. The momenta of more than two particles, however, can be added more generally using this sigma operator. Now this is the momentum as we know in classical mechanics, which is mass times velocity. But we need to find out that how this can take place, or can we take forward with this formula in quantum mechanics. Now as you see that these two things, the velocity times mass for a particular object and for n number of objects is the formula. But here you see that we deal with macroscopic scale. So when we are dealing with macroscopic objects, things are quite clear, things are quite deterministic. Also we have a precise measurement concept. That means given certain position, given certain conditions in Newtonian classical mechanics, we can understand and we can precisely measure where the particular ball or a particle is. We also know what is predictability, because the predictability shows that where that particle or particular object will move into, and that is why we know where it will be in the near future. So macroscopic scale, predictability, measurement, which is very precise, gives us a future prediction that where the particle or the object would be. This is the basic philosophy, this is the basic template, or we can call the basic tenet of how classical and Newtonian physics goes around, and these are being guided by Newton's laws of motion. But as you see, I have put a big but, because this is not the way which classical mechanics deals with. So when we find momentum in quantum physics, you see this is a kind of a wave, and it is given by this psi, that is a wave function. So it only tells that possible outcomes of measurements, such as an electron's possible position or momentum. Remember that it is only given a prediction that what is possible position or momentum. So these red dots on the bell-shaped curve actually shows that the electron can be here, it can be here or here. That means what it shows that in the entire spectrum of quantum mechanics, the position and everything, the time evolvement is being guided by Schrodinger's equation. Well, I'm not going to explain Schrodinger equation now because I will make a separate video on that. But what is important is this: the behavior of a particular group of particles is encapsulated by a wave-like entity. So what we deal is that we are just left with the mere chance of a probability of finding the electron with different values of momentum. Given this psi symbol, which is actually a wave function, we can only find the different values and the probability of finding the location of electron, which is far different from the predictable world of Newtonian physics, when we saw that momentum is precisely mass times the velocity and we get the value. So given this kind of a scenario where we know that probability is the square of the amplitude of the wave function, we can say that the electron or the subatomic particle might be lying over here, which is very unlikely, and this is a broader chance that it is likely to be here. So when we deal with classical mechanics, for example, if this is a ball, it is here now. Given certain conditions, we can find out it will be here later, right? So we can definitely tell that where it will be and where it will land up. Given this kind of a funny picture which I have made, just for example, it is here now, the electron, where it is located to be here now, we can never say where it is, but only and only we can get a complete range, or a range where there is a probability that the electron might fall within that range. So you see that the below mentioned figure is classical mechanics, where I can precisely find out where the particle would be. But for a quantum mechanical world where only we can find the probability, we get a range and we can find out the particle may be in that range. But to be very honest, what happens that when we make a precise measurement through our instrument, what happens is that wave function collapses and we are left with only one probability where it states what is the quantum state. Well, about wave function collapse, I will be making a separate video, but I've just mentioned a little bit in my early beginning videos what is a wave function collapse. For the time being, let us understand that we are only given a range, and this range can tell us a predictable manner or a predictable future where this electron would be, and as soon as the wave function collapses, we are left with one possible state where that particle would remain. So if it is here now, we also know that the wave function over time, if I pass this is the time, the wave function or the range also changes. So we get a lower range, we get a higher range, and with time evolution the range changes, and this is being guided by Schrodinger's equation. The Schrodinger equation, which is the basic, I would say, the pivotal force around which the entire realm of quantum mechanics flows around, actually gives the time evolution factor. That means how wave function evolves over time. As the time passes, the wave function changes, so the predictability factor also changes and the range also changes. This is something very typical to quantum mechanics, but it is not found in the classical deterministic world. If we find the position of a particle, we will be finding it there. With evolution of time, nothing will change, but here the wave function changes with the evolution of time, and that is being dictated by Schrodinger's equation. Okay, so now we have understood that what is a basic difference, how classical mechanics and quantum mechanics deals with momentum. It is now right time to move into classical and quantum mechanics and look into what quantum mechanics gives us in terms of momentum. So here is a nice familiar formula you're all aware about when we talk of classical mechanics, but when we talk of quantum mechanics, momentum is given by this kind of a bizarre equation. We are going to take time to explore this equation because this is what momentum is all about. So just to tell you and explain a little bit on this P is basically called a momentum operator. Now you might right now question me that what is an operator? I will make a separate video on operator because, as I tell, that quantum mechanics is very mathematical, so each of them requires a dedicated video and dedicated explanation. But for the time being, let us understand what is an operator. For example, if I have got a fever and I am using a thermometer in order to find the temperature. So the thermometer acts as an operator on the body, which is me, which has got a fever, and I can find out what the temperature is. So operators are something which will give the value of the system, but it is not like the operator, for example, velocity momentum in classical physics. There has got a lot of changes and it carries different meaning. I will make a separate video, but let us understand that this classical mechanics position momentum is being replaced by what is called a momentum operator. Well, I really don't want you to fall in fever. I want you to stay happy and healthy and continue learning quantum mechanics from these videos. So this, as we know, is a wave function. Now this lambda is called what is called an eigenvalue. Again, I will make a separate video on eigenvalue, but let us understand eigenvalue is something where the value of a measurable quantity associated with the wave function is being measured. So something once we measure gives a result, and that is called an eigenvalue. It's a wrong definition, but let us take it for the current understanding. So to find the momentum of a particle in quantum mechanics, first we use the momentum operator. We apply to the wave function psi and then find the eigenvalue, which is the experimental results. So this is just an introduction, kind of a basic layman's approach or understanding of momentum in quantum mechanics, but I will be just talking it a little bit more. But let us understand this is how the equation or the entire concept of momentum looks in quantum mechanics. Okay, so we take this equation further, and you see that the lambda eigenvalues represent the possible measured values of the p operator when we are using this operator. Classically, lambda would be allowed to vary continuously, which generally happens, but in quantum mechanics, typically lambda has only a subset of allowed values. So now the question is that once we understand, okay, let me go back, we understand that we are using an operator, which is this one, p with a hat, and I'm applying this with a psi operator, which is the wave function. Don't worry about those curly brackets, we will explain what is a bra and a ket later. And this gives us an eigenvalue, which is this lambda, and this is what is being measured. The question lies that can we use this kind of a similar equation carrying the momentum operator from classical mechanics and directly substitute into the familiar P equal to mv formula of classical mechanics? The answer is a big no, and we will soon see why. So momentum or linear momentum in quantum mechanics is given like this. Now, what is this all about? It has got a minus I imaginary number followed by the reduced Planck's constant and d by dx. So let us find it out what it is all about. So this is the momentum operator, which we understood. Now this minus I is actually imaginary unit. Now what happens is that this is the reduced Planck's constant and these are the partial derivatives. So this is a kind of a component by component understanding of the momentum part. Okay, so this P, I would say the momentum operator, when it is applied to the operator to the wave function, and here we apply the operator directly to the particle. So what happens is that this minus I and the entire momentum concept comes because we are applying the operator not on the particle but on a wave function. Whereas we consider P equals to mv in the, what I would say, in the classical mechanics, then it is directly applied on the particle or the object, and we calculate by taking a product of mass times velocity. So it is this operator which being applied to a wave function yields to this kind of a result, because we are not dealing directly with the particle, we are dealing with the wave function which evolves with time guided by Schrodinger's equation. In classical mechanics, we deal directly with the particle and we get a product of the mass times velocity and thereby getting the momentum. So I hope that you are getting things clear. So calculating momentum in quantum physics is not a very easy, straightforward that you calculate a mass and multiply it by the velocity and you get it. So what you need to do is to have a kind of a momentum operator apply to the wave function calculate it with the derivative and get that imaginary unit also under your sleeve. Okay, so in order to explain what this I is all about, I would consider a simple plane, a simple kind of a wave, right? And I will take the wave function, or I would say the exponential, the simple wave equation which we have got. Now this, or we can take this one, because I have just for simplicity taken it in a one dimension. So you can take the x as a position and time. So what happens is this E is the exponential, which is actually responsible for the shape of this wave. Now, those who are aware about exponential, you already know the exponential looks like this, and the exponential you see in this below this curve, there is a real part and the imaginary part. You might have a question that although this doesn't looks like a wiggling wave, but is it that the exponential gives rise to that? The question is yes. This I equals to square root of -1 actually provides something into a wave. It is not that simple, which I'm explaining it right now, but eventually I will make a video and you will see that this negative square root of -1 minus 1 is basically the imaginary part, and when it is coupled or multiplied with the exponential and followed by the position, and we will see what it is, this actually turns into a wave. So the responsibility of becoming a wave and thereby exploring the quantum laws is basically due to that. Okay, let us move on further. I will just explain this one. This is actually the momentum. This is the position which we considered it to be x direction, just taking it in a one dimension. This is the particle's energy and this is the time. So if I take a kind of an arbitrary curve, now this one, this equation, you might say that this is very much applicable to a plane wave, like a simple wave. But there is a good news. The good news is that if you take a kind of an abrupt wave like this, and I take the similar wave like this, then we can use this equation to slowly divide it into P1, X1, E1, T1, and then P2, E2, X2, E2, T2, and so on. That means we have a mechanism in which we can take any arbitrary wave and add it with this wave function and get the results. Okay, so what we are going to do is that we are now going to see that how we are coming to that equation of momentum. So what we do is that we take a derivative of this. So we are taking a partial derivative. So just to take a pause and make you understand why we are taking a partial derivative, because partial derivative as usual takes the gradient or slope of a particular function, but we are not worried about the slope right now, the gradient. We just want to find the t. So here you see we have taken a partial derivative followed by the exponential factor, and here also the original wave function is there. Then we get this, and finally we get this. Now if you arrange these two equations, then we get to this factor, which is the momentum, and that is how we did momentum in quantum physics. This is the momentum operator, and remember that when you're using this P momentum, I have substituted this psi, the lambda 1. So what is that? This P is the momentum operator, and we're making a measurement, and this is the measuring the result, that is the eigenvalue. Although it is not that simple and straightforward, however, this is basically giving you an idea that how we arrive to the momentum formula and how we do it using a plane wave function. Actually, to be honest with you, this plane wave function, if you look into the derivation, it comes from the de Broglie's wavelength. Yes, it comes from de Broglie's wavelength, and then we take a partial derivative followed by the exponential and multiply it by this I factor. This I factor is also common in general wave equations, so that is why we get this I. And I have just recently made a video with complex numbers, why it is important in physics, quantum physics, followed by imaginary numbers. Now you can see, you can well relate that video with this one. So if you're going through this video, I will also request you to watch my other video, which is called the mathematics of quantum physics, that you can find out those things and you can get a better idea. Okay, so now we are going to dig a little bit more deep into momentum, and we are going to take certain mathematical examples. Now, if you have watched my earlier video, where I spoke about normalization and why normalization is important. I showed two examples, one with Gaussian wave packet and another with Schrodinger's equation. I just want to remind that we dealt with these two equations and we came into this equation, right? This equation, the green one right at the bottom, we are going to take it forward and we are going to explore a little bit more, which is very relevant and very important. So if you have not watched my video, please go and watch my video on normalization, because that is also important. Okay, so what I would like to tell you is that this one, for a particle in a state psi, the expectation value of x is given by this one. Now, what does this exactly mean? Now, obviously, it doesn't mean that if you measure the position of one particle over and over and over again, the average of the results you will get is the same. No. On the contrary, the first measurement, whose outcome is more or less indeterminate, will actually collapse. I was talking about collapse of the wave function. Same thing, collapse the wave function in a spike at the value actually obtained, and the subsequent measurements, if they perform quickly, that is important, if they perform quickly, they will simply repeat the same result, right? So I would repeat that the first measurement whose outcome is indeterminate will collapse a wave function and form a spike in the curve and at the value actually obtained, and the subsequent measures, if they are measured correctly, will simply repeat the same thing. Rather, we would say that this x is the average of measurement performed on particles all in the state psi, which means either you must find some way of returning the particle to its original state after each measurement, or else you will prepare a whole collection of particles, each in the same state psi, and measure the position of all of them, where x is the average of all the results. Okay, so that actually shows that if we are dealing with a particle in the state psi, what could be the expectation value, and how x and is the average measurement, and how psi is called basically the state. So here is most important. The expectation value is the average of repeated measurements on an ensemble of particles or on a prepared system. So we move on next, and what we get is that, as I was talking, that as time passes, the entire distribution or the range changes. So as time goes on, x will change because of the time dependent of psi, and it might be interesting to know for us. We want to know that how fast it moves. Now we take the equation of this and this, right? And what we get is this one. Right, so this is basically what I'm doing, is that I'm integrating those parts, and then I get into this, where I know that the product rule actually says this. So you can just check on the calculation. I'm just doing a part by part integration because I really want to know how it all moves and how things happen. So I will take the product rule from this screen to the next part. Right, here it is, and I have just skipped one of those parts just to make the integration simple. So I got this, and then I get this one. Now what is important is that we are talking about the velocity of the expectation value of x, which is not the same as the velocity of the particle. Nothing we have seen so far would enable us to calculate the velocity of the particle. It is also not even clear what velocity actually means in quantum mechanics. Very true, because we really cannot know what velocity is. If the if the particle does not have a determinant or a precise position, neither does it have a well-defined velocity. That's true. So all we could get is reasonably is asking for the probability of getting a particular value. And how do we do that in the probability density? That we will deal later. Right. So here you see that we got this equation. I skipped the integration part. This equation is something that we are talking. We cannot get anything about the velocity. We only get the expectation value of x. That is the we got the operator between the conjugate and the complex conjugate of psi, right? So it is not the same you can talk about the velocity of the particle. Because if the particle doesn't have a position, how could it have a velocity? How can do that? And it is not also clear that in quantum mechanics what velocity actually means. So moving further, what we can do is that once we write this part, this is the summary, right? The expectation value of the velocity is equal to the time derivative of the expectation value of the position. So here is a velocity, this is a position, and this is time. So what we get is that the expectation value only of the velocity, we get that, and that is equal to the time derivative of the expectation value of position. So once we write these operators, what we can say is this one. This equation actually tells us how to calculate V directly from psi, and once we write those things, the x and the p, we say that the operator x actually represents position, and the operator h bar upon I and the derivative, this is operator x represent position, and this one represents momentum in quantum mechanics. To calculate expectation values, we actually put a kind of a in between or sandwich the appropriate operator between the psi conjugated and the psi to integrate. So that actually brings us almost to the end of the video, because here we have looked into how we are writing the operator and using the operator to find out the momentum. Now, this equation looks somewhat similar to this one. I mean to say, this is not mathematically correct to mention them, but you see here also minus h bar, which was the general momentum. When it is plugged into this, it more or less looks same. So if you go back to my previous this one, this is important, that the expectation value of the velocity is a time derivative expectation value of position. And when further we find these things, we get that how the operator actually finds out the operates, and then how this part, the derivative part, represents momentum in quantum mechanics. So I know that operator itself is a important and a challenging part, because it requires a mental shift of mind to understand. So I hope that this part of the momentum part is clear, and this is just to equate how things are. So time to have a quick summary. So we dealt with classical momentum, how it is different from quantum mechanical momentum. How do we define momentum in quantum mechanics from the plane de Broglie's wavelength? When we come to the exponential, and the square root of minus I along with the exponential is responsible for providing this wave, the use of operators, a little bit of eigenvalues, and finding the expectation values. So that's a quick summary that tells you us the story of momentum. And in my next video, I would be talking about operators, eigenvalues, and eigenvectors. So I hope you like this video. Please do comment and let me know what are your feelings and comments about this video. Please subscribe to my channel Physics for Students and click on the bell icon and click all to get all the notifications from Physics for Students. Don't forget to like also to my videos. Thank you very much for watching this video on momentum on Physics for Students. How momentum is dealt with quantum mechanics. I will be back with another video. Till then, goodbye and have a great week ahead.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.